Here 3 and 4 are in reverse order, I guess. There. If you go to the top of this.
Anyway, we got to equation 11, which was an equation that involved F1 and F2, but it was the angle average component. Now to compute F1, we're going to okay, first of all, all these are taus. Um, we're going to assume the tau is small and equate terms and keep terms that are first order in tau. And this is just totally out of order here.
It's because I think 3 and 4 are swapped. Should fall on 4. This page is not fine.
It's totally incomprehensible. I'm and I can't even. I don't even have room to write because it's all one block PDF. So what am I going to do? All right. This is a tau. We're going to use this collision operator. I showed you what it was for diffusion, but for simplicity, I'm just going to use tau now. And we assume tau is small, meaning scattering is rapid compared to the terms that generate anisotropy, so that it's almost isotropic. And I'm going to assume that v is much greater than u and neglect terms of order u over v. And then this is the collision operator. It's roughly equal to this, v times df dx mu. Now, let me just go back to show, if I can find it amidst all this chaos, to show you the terms that I threw away. F1, if I would have used equation 9 and kept terms, maybe I can write it in here. Use equation 9. Keep terms proportional to mu. Before there were terms, we kept terms that had no mu dependence. Here we put terms proportional to mu to the first power, and we get that f1 is equal to over tau is equal to well, and there's a minus here. And there should be a mu in here. Just a second. What was equation 9? It's impossible to scroll here. Yeah. So when we put f1, mu, f2, etc. into here, there's a term here that generates anisotropy, and it's v mu times what does it want?
Just minimize this to
Yeah. Okay, I actually went over this yesterday. First of all, why should there be an anisotropy caused by a spatial gradient? It's because more particles are coming in from the left at a given velocity than are coming in from the right, the same velocity. So there's always going to be a spatial origin, and the amount of difference, yeah, as Rahul knows, the anisotropy that's created per unit time. Well, the anisotropy is of order the mean free path over the gradient. So it's just Vx times times tau times df naught dx, right? The mean free path in the x direction is Vx tau. So the anisotropy, the term that creates anisotropy per unit time is just Vx mu over times df naught dx. And this, so there should be a mu in here. And that came from this term. If I have df, if I expand f in terms of f naught, well, v mu times df naught dx is generating, it's generating the f1 because more particles are flowing in from the left than flowing back from the right. If df dx is positive, then more particles are flowing backward from the right than in from the left. Now there was another term here which was proportional to du dx, which is also and actually it's a Compton getting factor. Compton getting was a person who co-authored a paper with Compton. And the point is when you're moving through something that has a velocity gradient, your motion means that particles coming at you are accelerated, are moving faster relative to you than the particles moving in back of you. Uh, so that's included in the expression for F1. It's already there. You're not making more. But when you're moving and U is changing, then this term is actually the change in the Compton-Getting factor. So that's why there's also a term that makes anisotropy. Now I'm totally lost. Yeah. Okay. So there's also a term here that's equal to minus. It just fucking disappeared. Where did it fucking go? I found it and then I moved and it fucking disappeared. If I can lift the pen off the goddamn screen without moving it, I'll be okay. This is where I want to be. Okay, there's a term here that's minus du dx times df naught dv, and I believe there's a mu in here as well. No, mu in here. But notice that this term is smaller than this term, because this term has a u on top and a v at the bottom, whereas this term had a v on top and nothing on the bottom. So this term is smaller by u over v compared to this term, which means we're only going to keep the first term when we write F1. And now we take this and substitute it back into equation 11, which had F1s floating around. You remember equation 11. There it is. There it is. There it is. No, oh, it's gone. There it is. Now if I pick the pen up, it's going to disappear, so take a good look at it. Did it go up or down? Did anyone happen to notice when I pick the pen up?
With mouse.
What? Yeah, right. That's why I use the mouse. Okay. Right. So this had F1s in it, but since I got F1 in terms of df naught dx, I can take a term like this and substitute it in back. And also this term also had an F1 in it, and
We just give first terms and that's it, right?
we use. Oh look, this is the thing I was looking for before, which had the second term in it, and I think that this is a mu. Alright, so what happens is this term v df1 dx, which was here, it becomes a second derivative in df dx. It, uh, it becomes this.
Yeah.
And this, how in the world did the f naught get denominator? Must have been a lot to her. Okay. Now notice that this term here is just the diffusion coefficient. And if you've ever heard that diffusion coefficients is just the velocity times the mean free path divided by 3, now you know where the 3 comes from. It was somewhere in there. Where did it come? There was a 1/3 here. And I don't remember where this 1/3 came from.
It's dimensionality, right?
Yeah, but I don't remember where I used it.
When you average over all angles.
Oh, when I averaged over angles, yeah, I got a 1/3. That's where it comes from. Okay, and as I already said, this was neglected in favor of this. And I went through a bunch of terms involving F2, and I don't think I'm going to torture myself by doing that in class. Anyway, I'm back here. Now, if I substitute 14 into 11, again, I get this, and this is a diffusion term. I get this because I had it all along. And I get this because it came... Okay, where did this term come from? It was proportional to du dx. And it was this. I mean, that's just what it was. It didn't change. So these two terms are still what they were, and it's just this term that changed into a diffusion term. And I'm left with these three terms as being leading order. And the reason I included all those other terms is just so you know that they were there, but they're small. But you know, when you think about it, just think about these three terms as being, and again, these are leading order when v is much greater than u, and when tau is fast enough that the distribution is kept isotropic. If tau is so slow that the gradients in x are well, if tau is slow enough and the gradients in x are large enough, it means that the velocity of the particle can change significantly just by moving into a new neighborhood. I mean, the relative velocity can change just because he moved into a new neighborhood. So he became the richest guy on the block. And if that happens, then you no longer have isotropy. The assumptions were that particles scattered before they changed their velocities very much. And if they change their velocities a lot, then the angular distribution also becomes complicated. It's not just the first order in cosine theta, but we assumed it was, and therefore these are the only terms that matter. And this is diffusion, this is convection, and this is compression. And this is the term that gives shock acceleration. Now, this equation can be written in 3 dimensions too. You just, wherever I put a ddx, you put a gradient, and you get the same thing. And here you'll get gradients, and
Yeah.
here you'll get the divergence of u, and here you'll just get the velocity vector u. But convection is convection, diffusion is diffusion, and compression is compression. And you can rewrite this. See, now here's where I start using capital F. F is equal to little f times p cubed. So here, finally, if I multiply by p squared, then, well, just a second. Log v is log p. Oh, right. So the difference in here is that u is inside the ddx. I think this should be f0 now. Where did it just go? The point is du dx, if the u is inside, I take du dx here, and I get f times du dx, right? Times f plus let's put the minus sign in, minus u times the f dx. Okay, if I multiply this by p cubed, the little f's become big F's. But here's the thing. That part's simple. I just multiplied this by p cubed. But the other change I made here is I put this u inside, and df d log p is now different because df d log p is p cubed times df d log p plus f d p cubed d log p and this is equal to p cubed times the f d log p plus 3. Now when I multiply this 3 by this 1/3, it cancels out this term here. So this is the same as this. I like to put the u inside because because then this becomes a perfect differential, and I can integrate through the shock more easily.
But you
Now,
also have divergence term du over dx.
that's right. That's
So,
fine.
so it's not okay.
Now, this equation, in this form, was written by Parker first in the late 50s. Uh, it's not clear to me he realized that you could apply it even when du dx is a delta function for a shock. In other words, this is this is a standard thing that's done in statistical mechanics. You assume the mean free path is small compared to the gradient, and you take first order uh, increments, and you proceed. The Chapman-Engskog method of deriving transport coefficients is basically just this. It goes from the kinetics to the fluid, and it equates terms that are first order in theta, and then substitutes them back into the angle average terms, and it gets transport coefficient. Same way we derive diffusion, that's the way they derive diffusion, and heat conduction and viscosity and things that depend on diffusion. And it's always assumed that the mean free path is small compared to the gradient. But it's not clear that Parker himself realized that you could apply. I certainly didn't realize it. That you could apply this equation even when the u dx is a delta function, even when u changes over scale less than the mean free path, because remember all we assumed was that u is much greater than v, and that the scattering was fast enough that you didn't have to worry about the higher spherical harmonics. The second spherical harmonic F2 was much less than F1, and because and if you went through all those other terms, you would see that it's perfectly good derivation as long as you respect u being much greater than v. So the idea is you can apply this to a shock now, where u is constant, u minus for x less than 0, and u is u plus for x greater than 0, and u dx is a delta function. It's proportional to delta x times the velocity difference. That's what du dx is. And now what you do is you solve the equation upstream and downstream separately, and then at the boundary you invoke this term. And let's see how that works. For u equals constant, I just have, when u is equal to a constant, I just have these two terms, right? U constant means the third term 0. So I have the solution, it's just a diffusion equation, d dx d dxf is equal to d dx uf.
Yeah, that's
Okay, here we wrote small f's, but it's also true for big f's, because there's the spatial derivatives. And this should be proportional to.
Yeah, but what is omega again?
Where's omega?
W.
Where's
That's
w? Oh, this is U.
Ah, that's U. Okay. Just why do have why do have their minus sign in exponent? Because if you solve this, you
Well, okay, if U is positive,
okay. Anyway, it should be
no, if U is positive, just a second. Yeah, you know what? Maybe this should be a plus. I do believe you're right. It's plus. Okay. All right. Now, which solution do we use upstream and which solution do we use downstream? Downstream, downstream x is positive, and
okay.
since the velocity is sweeping in this way, to balance it by diffusion, the diffusive flux has to be in the negative direction, which
So U
means
should be negative.
no. U is always positive by definition.
Ah,
I picked
okay.
the shock so that it flows from x equals minus infinity.
Okay.
It's flowing towards positive velocity. Now, if I pick this downstream, if I pick this solution downstream, it blows up to infinity well downstream.
Okay.
And I don't want that solution. Um, because there's no source of particles downstream that's allowing them to diffuse upstream. In principle, if I had a barrier, if I had a piston, it could. Then maybe I would need something proportional to this. But if I assume that the flow just flows infinitely far downstream, in the in the shock frame, you always look for a constant post-shock solution. It just flows towards infinity unchanging. If you go into the frame of a post-shock fluid in the frame, uh, it's supposed to just sit there and not change. Um, so we pick the constant solution upstream, but downstream we want the particles flux at minus infinity to vanish because the cosmic rays are being made at the shock. The energetic particles are being accelerated at the shock, and infinitely far upstream we assume that there's nothing but cold fluid flowing in. So we pick this solution for negative x and this solution for positive x. And now, once we have these solutions, we take equation 14, which I think it's equation 15 at this point. Is that what I said? I think I want 15 here. And we integrate from minus x to plus x, and then we get something that contains all three terms.
Okay.
And this should be a p. Alright, I have to go. To be continued.